Hello and welcome to Equity Education, the chemistry version, and today we're going to be looking at alcohols. Right, so again, like most of our organic, it's quite a big topic, but we'll crack on, and I'd probably advise you to have some breaks and just read through it as we go through, because there's a lot of information. Okay, so I'd like you to open your booklet and we'll start. So, general formula. So the general formula of an alcohol is CnH2n plus 1 OH. E.g., if I have C3, H2n plus 1 would be 2 times 3, which is 6, so 7, and OH. The structure, so our structure would look like this. And remember, R stands for an unknown carbon chain length. So in general, this is what the structure looks like. Functional group, as you're probably well aware, is an OH, and they have the suffix or the end of ol. E.g., got some examples for you. So I'd like you to have a go at naming or drawing them, whatever's missing. Okay, for the first one then, so we have, what have we got? We've got 2 carbons, so we know it's eth. And the ending is ol, because we have our oxygen here. This is propan 2-ol. Right, so the 2 represents the position of the OH on a carbon. So that must mean we must have 2 carbons either side. So 1, 2, 3, propan, 2-ol. And this, well, I know that my longest carbon chain is prop, because it's 1, 2, 3. I know that the position of my OH is on carbon 2, so propan 2-ol. And I also have a methyl group on carbon number 2, so 2-methyl propan 2-ol. Okay, so alcohols can be classified further. Alcohols are classified into primary, secondary, and tertiary. Oops, that doesn't really look like an R. Let's get rid of that. So primary, secondary, and tertiary alcohols. Right, so how do we classify these? So to classify an alcohol, count how many carbons are attached to the COH bond. So we're looking at this bond. How many carbons are coming off it? Yeah. E.g., so this is what we're looking at. And here, so we're looking at this. We're looking at this. And we're looking at this. Right, so in the first one, how many carbons are coming off this C which is attached to the OH? Well, it's 1. So I reckon that is probably primary. So you might see primary as this. So a 1 and a degree. Looking at this carbon OH bond, how many carbons are coming off here? 1, 2. So this is secondary. And lastly, looking at this bond again, 1, 2, 3 coming off. So this is tertiary. Pretty simple. Yep. Okay. Okay, so moving on. Physical properties. Okay, so boiling point. So we'll fill this bit in and then we'll go back and draw the diagram. So alcohols have a high boiling point compared to the equivalent, compared to the equivalent alkanes and alkenes. This is due to the stronger hydrogen bonding. which is an intermolecular force. If you're unsure about intermolecular forces, you'll have to watch the video on intermolecular forces, and this will give you some more idea between molecules of alcohols. E.g., so if we're going to draw this, let's draw H3C, so we'll draw methanol, so it would look like this. So this is my methanol, and I've separated out my oxygen and hydrogen, the alcohol group. And we know, well, you may know if you've looked at your intermolecular forces, that this is more delta negative, this is delta positive, 2 lone pairs here, 2 lone pairs here, delta positive, delta negative, and between these lone pairs here, let's do it bigger, we form a hydrogen bond. And this hydrogen bond is the strongest intermolecular force, which requires the most amount of energy to break out of our intermolecular forces, and that's why alcohols have a high boiling point compared to alkanes and alkenes, because alkanes and alkenes do not have hydrogen bonding. Okay, so boiling point increases as carbon chain length increases. There are more points of contact, which increases the strength of the, I'm going to put London forces. So you really need to know what intermolecular forces are, and students get confused in this, so all I'm going to do is draw a diagram. Okay, so we've got two molecules, two different types of alcohol. This one with more carbon chains, this one with less carbon chains. Now we've said that there's hydrogen bonding between our OH groups here. However, we still do have a London forces between our carbon chain. Okay, so these are London forces. So if I increase my carbon chain length, means I'm increasing the number of points of contact and therefore increasing the number of London forces. Now even though hydrogen bonding is the strongest intermolecular force, if I increase the points of contact, I will increase the London force, which still increases the boiling point of the alcohol. So even though alcohols have hydrogen bonding as their strongest intermolecular force, they always have London forces as well, which explains why when we increase carbon chain length, we increase boiling points. Okay, moving on. So boiling point decreases, oh no, that's what we've just said. So boiling point increases as carbon chain, no, let's read it properly. I'm reading the wrong bit of my notes. So boiling point decreases as number of branches increases. So this doesn't make any sense. As there are fewer points of contact, which weakens the London forces, e.g. if I have a molecule, an alcohol, which has a branched chain, there are fewer points of contact, therefore we have a lower boiling point. Some definitions which you've definitely probably heard before. So volatility is the ease at which a liquid turns to a gas, especially if you've looked at your alkanes videos. So alcohols are less volatile compared to their equivalent alkanes and alkenes for the same reason as boiling point. Longer chain alkanes are less volatile due to the above reason for increase in carbon chain. So we're still using the same explanations, but we're using volatility instead. And viscosity, the definition is a fluid's resistance to flow. Therefore, as carbon chain length increases, alcohols will become more viscous because we have more intermolecular forces, therefore making it flow less. Same reasoning, just different words. Okay, so some more definitions. So miscibility with water. So miscibility means the ease at which two liquids will mix together. It's usually the ease at which a liquid will mix or a solution will mix with water. Okay, and alcohols can form hydrogen bonds between the alcohol and water. So we say, therefore, they are miscible with water. If I was going to draw a diagram, it'd look very similar to the one I've just previously drawn, so I'll do it quickly. OH, H, O, H, O. So delta minus, delta plus, delta plus, delta minus, delta plus, lone pair, and then I form a hydrogen bond between my alcohol and water, which means they can mix together. Okay, so alcohols are polar and resolve in a polar solvent such as water. Again, I'm not going to go into too much detail. You can have a look into molecular forces if you want to know more about that. Okay, so the industrial production of ethanol. So ethanol is produced industrially by reacting ethene with steam in the presence of a phosphoric acid catalyst. So I have ethene as a gas, I have steam, so it's a gas, I add a phosphoric acid catalyst, and I produce ethanol. Okay, if it's steam, that means it's over 100 degrees, so ethanol must be a gas as well. Okay, so it's something you just got to remember. This is also called hydration, and you've probably seen this if you've just watched the alkenes video. So production of ethanol by fermentation and distillation. So we can produce ethanol by using glucose to produce ethanol plus carbon dioxide. So this fermentation process is basically how you make your drinking alcohol. So to get this, we need to use usually sugar cane, or something that has a natural fruit which involves glucose. The conditions are we need an aerobic conditions, which means without oxygen, temp of about 25 to 35 degrees Celsius, nothing above body temperature, because otherwise the enzymes will denature. And yeast is the catalyst, but really it's the enzymes in the yeast which are the catalyst. And I'm not going to go through this in much more detail. These are just basics that you need to know. Okay, so moving on. Reactions of alcohols. Right, so the important reactions that you have to be able to remember and use. So if I have an alcohol plus a carboxylic acid, will be an equilibrium reaction, I will form an ester plus water. Again, I'm not going to go through these functional groups much, because you should know that by now from our basic organic video. So alcohol, let's use the example of ethanol. So CH3 CH2OH plus ethanoic acid would produce an ester. Remember, my functional group of an ester is a R C double bond O. So this part is from my carboxylic acid. This is from my alcohol. I'll highlight that. So this is my carboxylic acid, this is my carboxylic acid, this is my alcohol, this is my alcohol. And if we're naming this, and I used a pretty rubbish example, but we would name it ethyl propanoate. So ethyl propanoate. Okay, so there's another video on forming esters and how to name esters. So the reagents we need for this are obviously an alcohol plus carboxylic acid, conditions, we need a concentrated H2SO4 catalyst, and in general we need to warm it or reflux it. Warm or reflux, it does work, it's better if it reflux. Okay, dehydration reaction. So a dehydration reaction is to remove water, and here we take an alcohol and we dehydrate it to form an alkene plus water. E.g., we'll just use ethanol again. C2H4 plus H2O. So I've taken my alcohol, I formed my alkene, and I've removed water. Reagents, obviously an alcohol and alkene. To get this, I would need either heat with concentrated H3PO4, or I could heat at 170 or 180 degrees with concentrated H2SO4. However, this produces multiple products, so isn't the best way to do any synthesis reactions. Okay, moving on. So combustion reaction. Again, I'm not going to spend too long going through this reaction, so we'll do a combustion reaction is a compound plus oxygen. Let's try it quickly. So compound plus O2 makes carbon dioxide and water, e.g. In fact, you can have a go at doing this one. Okay. Okay, I'm pretty sure you've all used ethanol. So I react it to get carbon dioxide and water. Remember, balance your carbons first. So 2 CO2, balance your hydrogens. I have 6 on this side, so 3 H2O. Balance your oxygens, so I have 4, 5, 6, 7. Remember, you already have 1 oxygen here, so you only need 3 O2. Reagents, alcohol plus oxygen, obviously, and the conditions are room temperature and pressure. Right, been through them very quick. You need to go over them, make sure you know what they are, and be able to apply them general equations to any equations which you get about them. Okay, so oxidation reactions. So, for an oxidation reaction to occur, we're basically adding oxygens or removing hydrogens, and we need an oxidizing mixture. There are lots of oxidizing mixture, but the most common one is potassium dichromate and sulfuric acid, which we can either write as this, so it's the same thing, or you may just see it as Cr2O72 minus H plus. So this is potassium dichromate plus sulfuric acid. I'll write that out. And these are all the different ways you may see it written. So the potassium has been removed here because it's spectator ion, it doesn't do anything. Okay, the conditions for an oxidizing reaction to occur are generally warm. We can reflux and we can distill it, but we only really need to warm. But we can put reflux or distillation, dependent on the product we want to achieve. Okay, so an oxidizing mixture, rather than writing out potassium dichromate and H plus, can be represented as square brackets O in an equation, just to simplify it, and that's what we will be using from now on in an equation / reaction. Okay, so right, a big table's coming up. So oxidation reactions of different alcohols. So depending on the type of alcohol and apparatus setup, different products can be formed. So if I start with my primary alcohol and I oxidize it, I will form an aldehyde. If I oxidize this, I will form a carboxylic acid. If I have a secondary alcohol and I oxidize it, I will form a ketone. If I try to oxidize this, nothing happens. If I have a tertiary alcohol and I try to oxidize it, nothing happens. Okay, so used a lot of different probably used a lot of different new words here. I'm going to keep adding to them as well. So if I have a primary alcohol and I add potassium dichromate, I can set up some apparatus called reflux. So if I reflux a primary alcohol, I will get a carboxylic acid. And this means that it has been completely oxidized. However, if I have a primary alcohol and I set up a distillation, I will get an aldehyde. This is called partial oxidation, which makes sense because we haven't fully oxidized it to a carboxylic acid. Okay, Now I'm just going to write some molecular formulas of my primary, secondary and carboxylic acids, but then we'll relate back to them. So if I use ethanol, I will get this produced, or this, dependent on what type of setup I have, reflux or distillation. If I have a secondary alcohol, such as CH3, CH3OH, I will get a ketone, which looks like this. You'll need these formulas or these structures in a bit to be able to do your equations. Okay, so if I oxidize a secondary alcohol, I will get a ketone. Now I could distill it or I could reflux it. However, it's usually done in reflux to make sure it's completely oxidized. However, if I really wanted to, I could distill it, because that would mean I could remove the ketone from the excess water. Okay, right, so, oh, and lastly, primary alcohol, a tertiary alcohol, if I oxidize a tertiary alcohol, nothing happens. Yep, so there's nothing that occurs. Okay, an example of a tertiary alcohol may be this. Okay, my structure. So an aldehyde has the general structure of RCOH, ketone RCOR, and a carboxylic acid RCOOH. Okay, and we'll do an example of each one. So CH3COH, we would call this ethanal. CH3COOCH would be propanone, and CH3COOH would be ethanoic acid. Again, I'm not going to spend very long naming these because you probably watched the video already on naming and functional groups. Okay, so just a quick recap. So a primary alcohol, if it's distilled using an oxidizing mixture, will produce an aldehyde. If it's refluxed, it will be completely oxidized and produce a carboxylic acid. Secondary alcohol can be refluxed or distilled and will produce a ketone. Tertiary alcohol will not be oxidized using potassium dichromate and H+. Okay, so talked about different reflux and distillation. So what's the difference? So difference between reflux and distillation. So refluxing allows for continual boiling and condensing to occur. The product is completely or fully oxidized. So here we have the reactant, so maybe this is my primary alcohol and my oxidizing mixture of acidified potassium dichromate. Heat up, turn into a gas. Now on the outside of this condenser is cold water, so there's a tube in the middle where the gas is. The outside of that is cold water, so it will condense back down. Turn to a vapor, condense, turn into a vapor, condense, and eventually it will become fully oxidized and therefore produce a carboxylic acid. Distillation, so this is an example of a distillation, allows for liquids with different boiling points to be separated from each other. E.g., so if I have my primary alcohol here and I add potassium dichromate and H+, I will oxidize it, but I won't fully oxidize it. I will partially oxidize it and turn it into an aldehyde. Okay, an aldehyde has a low boiling point, so it will turn to a gas before the water turns to steam. Therefore it will come down here, again cold water into here, and the gas will start to condense, and I will get my distillate out here. So we can just put that into words and say that aldehydes and ketones at lower boiling points than alcohols or water, therefore can be distilled off So basically we've answered this next question. So what physical property allows aldehydes and ketones to be separated from the oxidizing mixture under distillation? It's because of their boiling points. Why is reflux used when forming a carboxylic acid from a primary alcohol? I'll give you a couple of minutes to think about it. Okay, and I'm sure you've worked it out, and it's to make sure the primary alcohol has been fully oxidized. Okay, so moving on. So writing oxidation equations. So you'll have to refer back to this table that we have just written down. So a primary alcohol to an aldehyde. I'm going to give you the word equation and I want you to give me an example. So ethanol, actually no, I'll give you ethanol plus O gives me ethanal plus water. Primary alcohol to a carboxylic acid, so we'll use ethanol again, plus my oxidizing agent gives ethanoic acid plus water. Aldehyde to a ketone, so aldehyde to a carboxylic acid, ethanol plus my oxidizing agent goes to ethanoic acid. Careful here that there's no water. And secondary alcohol to a ketone, so let's do propan 2-ol plus O goes to my ketone. I'll give you the name of the ketone, propanone plus water. Okay, so I've given you the word equations. I would like you to come up with the chemical equations. I'll give you 5 minutes to work this out. Be careful about the balancing. Okay. Oh, I forgot to do the first one, so we might as well do that together. So ethanol plus oxygen. So CH3, CH2 plus oxygen plus my oxidizing mixture goes to ethanol, CH3, CHO plus water. Got to make sure that the hydrogens and the oxygens balance. So we have 6 hydrogens this side, we have 6 hydrogens this side, we have 1, 2 oxygens, 1, 2. So it is balanced. If we go down, that's not down, that's up. So if we go down, we have ethanol goes to ethanoic acid. Again, make sure your hydrogens and your oxygens balance. Okay, so 6. We only have 4 here, so it's why we have H2O added here, because we only have 4 hydrogens. And now we have 1, 2, 3 oxygens on this side, so we need 3 oxygens of our oxidizing mixture, and we just balance it using an O, so 2O, OH. 1, 2, 3. Ethanol to to ethanoic acid. This will be my functional group. Remember, C double bond OH. It's usually written as HO rather than OH because otherwise it's confusing between an alcohol and an ethanol group, an aldehyde group. Produces ethanoic acid. You see there's no water here, and that's because we have the correct amount of hydrogen, so we don't need to balance it using water. And then here we have propan 2-ol. This is my propan 2-ol. Forms propanone plus water. Make sure it's balanced. So we have 6, 8 on this side, 6, 8, and 1, 2 oxygens, 1, 2 oxygens. Okay, moving on. So, observation when acidified potassium dichromate. Observation when acidified potassium dichromate is used in an oxidizing mixture. Well, what we actually see is when something is oxidized, my dichromate ion is actually an orange color. Okay, and it becomes reduced, so it gains electrons to green. I'm not going to go through this redox equation yet because you don't need to know it. However, what you do need to know is that the color change for an oxidation reaction involving potassium dichromate is orange to green. Now, if I had a tertiary alcohol and I tried to oxidize it, there would be no color change because there would be no oxidation reaction. So the solution would just stay orange. Okay, again, lots of information in our organic videos, so I will go away, try to digest it, and then have a go at doing the questions below. Okay, alright, so once you've digested the information, you can have a go at the questions, then we'll go through them together. Okay, so we'll go through these questions. So propanol is heated under reflux using an oxidizing agent. Name a suitable oxidizing agent, so acidified potassium dichromate. Write an equation to show this oxidation reaction and name the products. Well, the first thing you need to do is identify whether it's primary, secondary or tertiary. Well, I know that propanol, I'll just do it here, looks like this. So I'm looking at what's attached here. So I only have one carbon attached, therefore it's primary. Now I know that if I reflux a primary alcohol, I'm going to get a carboxylic acid. So it must mean that I have propanol and I form propanoic acid. Make sure you balance it up. And propanol was heated under distillation using an oxidizing mixture. Write an equation to show this oxidation reaction and name the products. So again, I'm going to start with propanol, but I'm only going to get partial oxidation to produce propanal. Remember, this is our formula of propanal. And just as a quick demonstration, I will show you the functional groups. So this is what ethanoic acid, propanoic acid looks like, and this is what propanal looks like. And remember, in both, because I forgot to write as a question, in both reactions a color change from orange to green will be seen if we're using potassium dichromate. Okay, and well, that's it for alcohols. Right, again, a lot of information. I would suggest going away, reading that, and doing some practice questions on them. But again, as always, I hope that was useful, and I'll see you next time. Okay, bye bye.